Okay, so we've got some Unit 3 extras right here, and one of them I'm just going to run through. Two of them I'm going to have you guys look at and see what you think the answer is. Just three quick multiple choice questions, things to kind of squeeze in from Unit 3, and then we're going to do a little bit to prep us for Unit 4, and hopefully you read Chapter 11 and you have some ideas. All right, so what we're looking at is a printout, and I'm just going to jump to the question. Sometimes that's what I do. Is I say and the question itself will maybe give you enough of an idea. Which of the following values represents the predicted change in height of the tree for each 1 meter increase in the diameter of the tree? So it's maybe I go back to the original words up at the top. So it looks like there is a least squares regression line for relating the height and diameter in a fully grown tree. So if you have a plot of this made, we're predicting the height from the diameter. And that makes sense because we can easily measure the diameter of a tree from the ground, but we can't measure the height very easily. So we want to kind of have a good idea of the height just from the diameter. Okay, so the question is, what is the relationship? So this is a computer printout. Remember, one of these, and here this represents something we're going to look at later, so we're not worried about that right now. We don't care about the standard error or anything of that. This is called a t-value. We'll worry about that later. So basically it comes to this, the estimate. We have the intercept. So this right here is my A, and that means this right here is my B. So my regression equation is y hat equals 5 plus 30x. So the question they're asking, what is the predicted change in height for 1 meter increase in the diameter? Well, that's the definition of slope. So we're looking at not the 30x, just the 30 itself. So it looks like my slope is 30. We would predict 30 meter increase in height for every meter increase in the diameter of a tree. And that's it. I mean, it's really just asking you, it's almost an interpretation question for slope, but no calculations required in this. Okay, that one's pretty straightforward. I just ran through that one, and hopefully you didn't even need to see that. But with this one right here, this is one, I don't want to spend too long on this, but we looked at a problem like this one before. So I know x bar is 5. The standard deviation of x is 4. Y bar is 10, and the standard deviation of y is 10. So we have 4 equations. We don't know what r is. It's a mystery. So let's try and figure out which of these equations over here is even plausible. And does anyone remember a first step we could do for a question like this? I'm sensing there's if I was to guess right now, I'd say most of you in here are like, oh, I almost know what I'm supposed to do on this problem, but I don't want to speak up because I can't 100% think through it. And I imagine there's a lot of people that are right there. So remember that the equation for slope is r times the standard deviation for your y over the standard deviation for your x. And we know these two numbers. Standard deviation of y is, so I don't know r, but I know that's going to be 10 over 4. So basically it's going to be 2.5 times r. And what do we know about the correlation coefficient? What's one thing important we know about the correlation coefficient? What's the biggest value our correlation coefficient could be?
It's between -1 and 1.
There you go. That's important here. So what we got is a situation where our slope has to be between -2.5 and 2.5. So we know that much. We don't know any more than that, but that's enough for our problem. So I can rule out any problem that has a slope bigger than that. So this one and this one, I have to rule out. Those both have a slope of 3, so that's too big of a slope. The next one is 2.5, which is probably not likely, but it definitely technically fits inside of our range. So we're good to go. All right, now the other thing to remember is that your regression equation y hat equals a plus bx always passes through y bar x bar. And now we just need to plug in these two values into our remaining 3 equations. So I'm going to get rid of this. I've ruled out 2 of them. So now I want to just look at these 3 equations and plug in my x bar and y bar. If the equation comes out to something that's possible, then it's a plausible regression line. This is not saying that's the actual regression line. It's just a possible one. Okay, so let's look at plugging 4 and 10 in for our standard deviations. So I got 10 equals 5 plus 2.5 times 4. Oh, I'm sorry, I'm using the wrong numbers. That shouldn't have been 4. Should have been 5. All right, so I'm using these numbers right here. I was accidentally looking at my standard deviations. Not those up top. All right, so hopefully I didn't confuse you. So if you're with me, I can plug that in. 5 times 12.5, that's going to give me 10 equals 17.5. Well, no, that's not true. So this does not work. All right, so let's try another one. So I could do x bar, y bar. I could do 10 equals 8.5 plus 0.3 times 5. And this gives me 10 equals 8.5 plus 1.5. And it looks like this one works. 10 equals 10. Yeah, that's good. So this one seems right, but due diligence, we're going to look at all 5 of them. And so if I try the last one, I get 10 equals 10 plus 0.4 times 5. That's 10 plus 2. So in the end, I get 10 equals 12. Okay, that one doesn't work. So there we go. We've got our answer. It has to be D. All right, so that's just a good reminder on this. Hopefully seeing it the second time helps. I can't predict what types of questions you're going to get, so I can't just give you like 100 types of every problem unless you want to be doing nothing but statistics all your life. But that's why I encourage you to look through those progress checks. You'll get a big sampling of all the different types of questions that are possible. And anything that you don't understand, you can bring those back to class and we can go through any of them. Okay, so let's look at the last one. Wait, there should have been one more. Oh, I skipped over one before. All right, so just look at this one real quick and see if you can come up with an answer to this. I bet everyone can come up with an answer. We'll see which one's correct. All right, so everyone focus in on B as your answer. So we know that, and I'll just talk about this. We know leverage is anything that's changed in the, not the Y, but the X direction. So I'm sure everyone picked up on that. So you knew this one was not part of it. So that's good. You ruled that one out. You ruled that one out. So it comes down to 1 and 3. 1 says a point with a large residual is an outlier. 3 says the removal of an influential point from a data set could change the value of the correlation coefficient. I think 3 is definitely true. So I'm with you on that one. So I'm going to cross out 1 only because I think 3 has to be part of it. The question is 1 true? A point with a large residual is an outlier. And I'll go ahead and tell you right now, actually, the answer is C. And I'll explain why, though I do completely understand why you guys all focused in on D. And that's not bad thinking at all. So what you have to remember is that a large residual is not a precise term. Or sorry, yeah, a large residual is inexact. All right, so look at this. I've got a bunch of things here. And I've got one right here, one right here, one right here. So right here, if I look at this point that was right next to it, that has an incredibly small residual. So, I mean, it's almost right on the line. This one right here has a much bigger residual. You might even call that a large residual. Would you call that an outlier just because it has a large residual? Not necessarily. All right. So these are pretty large residuals. And let me actually change this also. Let me pretend instead, I'll still have a few of these dots, but I'll try and erase most of it. All right, now imagine that your scatter plot is one where all of your residuals are kind of spaced out like this. So hopefully you can see the point I'm getting across is that a large residual in and of itself is not necessarily sign of an outlier. So large residuals and outliers are not necessarily synonymous. So anyways, that one is not true, though it can be true. All right. So there we go. If you have any questions about that, hopefully it's clear enough now. But if you still have questions, any of this stuff, we can come back to it. But that was just some wrapping up on Unit 3. Now we're going to jump into Unit 4. And if you read the chapter, you're going to already have a pretty good idea of what we're talking about today. And just to get started, I wanted to prime you with this scenario. This is almost based on reality, all right? But I changed it so that it fits statistics a little better. So I do like to go camping on a particular beach in California with my family. It does have 4 campground loops, believe it or not. So so far, so true. But, all right, I made up some numbers, made up some other things. So there are 4 loops for campgrounds. And when you make your reservations, in this scenario, campgrounds are assigned randomly. They just email you back and say, you're going to be at this campsite. So in this scenario, how many times would I need to go until I camped at every loop at least once? And it's kind of a rhetorical question right now. I'm not expecting you to jump out with an answer. I just want you thinking about that for a second or for a while. How many times do you think I'd have to go camp until I get to go camp at every single loop? All right, I'll just pause to let you think about that for a little bit, but you don't have to answer right away. So let's return to this. But what I wanted to do is I wanted to show you guys these 2 outcomes from flipping a coin. So in one of these, and I'm not going to tell you which, but I've got 2 sets of data. And in one of these, I flipped a coin legitimately. What is this, 20 times? Yeah, I flipped a coin 20 times and came up with my outcome. The other one, I made up results in my head. And I'm going to see if you can identify which one of these, and you can circle the table, which one of these is the real coin being flipped. So the one on the right, like I said, is the true coin. And here's the thing. This is kind of a brief aside. It doesn't relate to the rest of what we're going to do, but I think it's worth talking about. True randomness, like if you really flipped a coin 1,000 times, that would take forever, but you're going to get certain results. You're going to get a situation where, if you notice this, I got 1, 2, 3, 4, 5, 6 heads in a row. And that was a real coin flip string. So I got 6 heads in a row. Now, when people make up their own outcomes, normally they'll only go as far as like 3 in a row. And then they're like, well, I need to change over. And that's kind of what you were saying, Matt, that true randomness could be, I could get 20 of these in a row. And that will happen eventually if I flip a coin long enough. So randomness will have longer strings than longer strings of one result than pseudo randomness will, this made up results right here. Though I do appreciate all the conversation and the discussion that you guys were having and the thought processes that were going on. Okay, so that is random. Okay, so when you really flip a coin, and even there, you could argue that that's what's called deterministic. Because if you knew how much force you hit it with, where exactly you hit it, where it pivoted from, if you knew all the variables, you could determine how it's going to land. But let's just say true randomness is almost impossible. Like I said, this whole stuff on randomness is just for fun. I think it's kind of interesting, but your mileage may vary. So what we call random frequently is not random, and it's what we call deterministic, but it's certainly unpredictable enough that it functions the same as true randomness. So when we talk about things being random or randomly selected, okay, it's not truly random, but it's random enough that we don't really know what results we're going to get. Okay. So the kind of randomness that we use is referred to as pseudo-random. I'm going to show you some things you can do in your calculator for randomness, and even that is pseudo-random. Okay. So an outcome is random if we know all the possible values it could have, but not the particular value it's going to take. All right. So if you were picking a lottery ball from you might have seen, or a bingo ball from like one of those cages, you know that it's going to be some kind of a coordinate for the bingo card, but you don't know which one you're going to pick. All right, enough about that. We do simulate randomness in statistics, and we're going to have a few different methods. And we're going to talk about when it comes down to sampling, trying to get results from surveys and things like that. That's next chapter. But if given a specific event with a known probability, if we wanted to generate a set of random outcomes, we have options. And I'm going to go through those options real quick. This is one that is very antiquated, and a lot of stats teachers will tell you we shouldn't even cover random digit tables. It's unlikely you'll need to worry about this for the AP test, but it is theoretically possible, so that's why I'm going to talk about it. Random digit tables are obviously not random, because I know every time I turn to this is from your textbook, every time I turn to this page, I'm going to see a 9, 6, 2, 9, 9. It's going to be the same numbers every time. But if I go to a random digit table, and I go to a random spot, I can just start, if I started right here at the 1, 1, 7, 2, 0, 2, 9, 9, 9, 9. So there are 4 9s in a row right there. 7, 3, 7, 7, 3, 3, 3. So that's random as far as we're concerned. So random digit tables are possible, but maybe a better option is what we call random integer on your calculator. So this is where you'll want to have your calculator handy. You have to hit your math button, and you go over to the very last option, which is probability. You can see it on your screen right there. And the option you want to go down to is number 5. And you have 2 ways of using random integers. Because when you first get this, it's going to go back to your main screen. If you can see what I've got, it's just well, there you go. You can see it. It's just random integer with an open parentheses. So you can just put any 2 numbers that'll define your range. Let's say we want to pick a random number between 1 and 100. So I'm going to do 1, comma, which is just above the 7, and then 100, close the parentheses, and then I can hit enter. It's going to give me a random number. And I can do the same thing over and over again. I can just keep hitting enter, and I'll get a different random number. And we can define what range of numbers we want to go through. So there we go. That is a way of generating random numbers. Now, there's another thing we could do. If you go back to math, probability, random integer, if you do a new random integer, you could do 1 to 100, but let's say you wanted to get 3 numbers that were all random. So I could do 1 to 100 like this. Sorry, it's down to the bottom. 1 to 100. And then I could do another comma and put 3 in. So that's going to generate 3 random numbers between 1 and 100. So if you try that, that's 1 comma 100 comma 3. Then you'll see 3 random numbers generated. I happen to get 2 of the same number in a row, which is possible with randomness. Okay, so your calculator, could you Okay, can we go through that one more time? So just to get to random integer, you have to, from the main menu, hit math. And then you have a menu pop up. You want to scroll all the way over to the right where it's PRB, that's probability. And then random integer is number 5. And that just opens up the random integer option on your calculator. And that's where you can plug in whatever range of numbers you want to pick from, whatever integer range. So if we need to go for some reason between 24 and 83, I could set that as my range and it's going to pick a random number between 24 and 83 if you look at the bottom there. All right, if you still have questions, there will be time. You can, I can help you walk through that. There is, okay, actually, and there you can see the results. I forgot I had this slide. So there we go. 3 numbers drawn from that so you can see kind of how it looks. All right, the other option that we could use, now there are other options besides just this, but if you do go back to math and then probability and then down, if you just do the first one, which is rand, that is going to give you a random number completely that'll be like a decimal. I think it actually goes between 0 and 1, but I could be wrong about that. We don't really use it, so don't worry about just random on its own. But if I go all the way down to the very bottom, number 8, there's random integer no repeat. The problem with this one is that you have to do a random integer string and use every single number. So I would recommend not doing a random integer no repeat from 1 to 1 million, because it is going to have to generate 1 million numbers, and that might blow up your calculator. I'm going to try it real quick. It won't let you do it. Okay, it knows it'd blow up the calculator, so it won't let you. Okay. So anyways, random integer no repeat. That's best if you only have like a few numbers you need to worry about. Here's 1 through 5. You could go to 1 through 100. And of course, you're not going to see, even this takes a little bit of time, you're not going to see all 100 numbers. But if you only need the first 8 numbers or so, you can see these numbers being drawn, that there's no repeats. All right. So I don't know if you do need some more help with that, we can go through it. Anyways, that is kind of the fast way. If you need to get a random number, your calculator will handle that really quickly. Okay. So knowing that we can generate some random numbers, let's go back to this scenario. We got the certain amount of campsites. We want to find out how many times are we going to camp on this campground until you've stayed in every loop at least once. So at this point, what are just some general thoughts for what we could do here?
One thing I noticed was that there's gonna be a higher probability of ending up in the later campsites like C or D because there are more spots that you can
Yes.
get.
And that's absolutely right. We're almost jumping ahead a little bit into probability, but we're not quite there. That's going to be next, and you'll love that when we get there. So I want to focus on the fact that these campgrounds are assigned randomly. And we just talked about random number generating in our calculator. So kind of just focus on that kind of train of thought. What could we do here? So this question might just simplify it a little bit. What is my end? What number am I looking for? So do I care about which campsite I end up in on any particular trip? Does that matter to me?
No.
No. So the particular campsite anytime I go doesn't matter for this question. So what number does matter? What is the answer, quote, answer to my question?
When you'll stay at all 4.
When you'll stay at all 4. So maybe we think about it this way. What's the fewest number of times I would have to go to be able to stay at all loops?
4.
4 times, yeah, obviously. So stay at each one of these one time. So that would be ideal. Now it's unlikely to work that way. So how many times do I have to go? That we don't know, okay? And if we did this over and over again, we might have to go a different number of times. Maybe one time I get it in 4, I go 4 times, I stay in all 4 loops. But then another time I stay in loop D because it's the highest probability. I stay there like 5 times in a row before I ever go to a different loop, right? So anyways, what we're looking for is a way of simulating what happens without having to go repeatedly and just randomly get a campsite. All right, so look at this, and maybe this will help guide your thinking. This number range right here, what if we thought of each of these campsites as a numerical outcome from a random number generator? So how could we kind of set that up? First of all, how many campsites do we have total?
95.
95 campsites. So let's just imagine here, I randomly generate a number between 1 to 95. So now we're really kind of getting to the heart of this. What numbers could correspond? What numbers would we say means loop A?
1 to 10.
1 to 10. There you go. I'm getting it in the chat too. All right. So now you can probably see where we're going with this. What range would we pick for loop B?
11 to 25.
Okay. Next one.
26 to 55.
26 to 55. And that means, of course, we have to go. I'll just fill that one in. Probably everyone can see where that's going. All right, so we can randomly generate numbers, and we can just figure out how many times it's going to take until I get to stay in all 4 loops. Okay, so I'll just do this real quick. I'm going to randomly generate. I'm going to math, probability. Oops, picked the wrong one. Math, probability. I'm going to do random integer between 1 and 95. I'm not worried about repeats because I might get assigned the same campsite over and over again. So my first one, I stayed in campsite 31. So that puts me in loop C. The second time I got 14, that puts me in loop B. The next time I got 53, oh, I stayed in loop C again. Then I got 78, now I'm in loop D. So now I just need to figure out how many times until I get to stay in loop A. That's gonna be probably the hardest one to get. So you can see my check marks just mean my results that I'm getting. 60, 56. All right, 60. You can see what's happening. I actually just want to try and finish this, but man, it's taking a sweet time. There it is. Finally, I finally stayed in loop A. This took me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times. So for this simulation, it took me 12 trips to the beach until I stayed at all 4 campgrounds. Okay, so knowing what to do, what I want you guys to do is do the same simulation, and my 12, I'm going to put a dot right here. I want you guys to do the simulation, and because there's so few of us, see if you can run the simulation maybe a couple times and just add some dots and figure out how many times it took for each of your simulations until you got to stay at all 4 campsites. I'll put those numbers up on the screen again so you can remember what your number ranges are.